Hello dear children, in today's class we are going to start the new chapter, that is sound. Dear children, in this chapter we have mainly 3 units. In a unit A, mainly we will be focusing on echo and the numericals based on echo and its applications. Whereas in a unit B, we will be talking about the types of vibration. There the very important thing is that resonance and its applications. Whereas in unit C, we will be discussing about the characteristics of sound. Whereas children, in today's class particularly, we will be discussing the unit A of the sound chapter. Dear children, as I told you that in this chapter, the main topic is echo actually. But before going to discuss what is echo and what are the conditions of echo and examples for that, and moreover the applications based on echo. So let us hear the basic concepts related to the sound. Children, what do you think about the sound? Of course, since morning to evening, we will come across with the many types of sounds actually. In that, some sounds will make you happy, some sounds will irritate you. With that, we make it sometimes frustration also. Of course, it's quite natural. Am I right? Yes. So children, what is meant by sound? So first, let us see children. So let us see a few important points regarding sound. Children, we all know that sound is one of the forms of energy. Can you agree with that? Yes. So here the first important point of sound is that it is a, let us write, it is the form of energy. It is a form of energy. Very simple thing. It is a form of energy. That is fine. And children, what happens when this form of energy reaches our eardrum? What happens? We will get, what is that? A sensation of hearing. So this is a form of energy which produces in us. What it can produce? It can produce sensation of hearing. So it can produce sensation of hearing. So in the simple terms, children, if anyone will ask you a question, what is a sound? Sound is a form of energy which produces sensation of hearing in us. That's fine. Then how sound is produced, children? Can you guess? Yes, children. So here, sound is produced by vibrating bodies. I mean what? Vibrating bodies can produce sound. Very, very, very important. So vibrating body can produce sound. That's fine. But here the question is that, can we hear the sound produced by vibrating bodies? All vibrating bodies, children. Just think once again. So it's very clear. So vibrating bodies will produce sound. That is fine. But can we hear the sound produced by all vibrating bodies? For example, grass, when wind is blowing, grass will be vibrating, children. Can you hear that sound? No. Now look at here. Here is a pen. Now this pen also vibrating. Can you hear this sound? No, you can't hear. Means there will be a limit. That we know very well. So children, so based on that actual limit, if you can see, the sounds which are less than 20 hertz, so these sounds only we can call it as a infrasonic. These only we can call it as a infrasonics, which are not audible to us. Whereas the sound with greater than 20,000 hertz frequency, these are called ultrasonic. Ultrasonics. Children here. So infrasonics and ultrasonics, these sounds can't be heard. So we have a particular limit. There is a range for us. What is that range, children? Yes, we have 20 hertz to 20,000 hertz, children. So this only we can call it as a audible. It is also we can say so audible sound. Or else simply we can say the sonic sounds it is. Am I clear, children? So the sounds with a less than 20 hertz frequency are called infrasonics, can't be heard. The sounds with greater than 20,000 hertz are called ultrasonics, which are also can't be heard. Only we can hear the sounds with a frequency range between 20 hertz to 20,000 hertz are called, it is actually audible range of range frequency of the audible sounds which can be heard. So children, this is a minimum basic knowledge regarding the sound. That's fine. Children, as we all know that yes, sound can propagate in the form of wave. So now let us recall once again about some concepts, some basic words, related terms about the wave. Let us see once again, children. So first, children, what do you think is a wave? Children, once again let us recall. Children, in a 9th class only, hey, don't forget that. Once upon a time, there was a 9th class. There we learned chapter called propagation of sound. There also we have learnt basic concepts, basic terms related to the sound. Am I clear? You may feel, sir, okay, we learned long back, why are you taking out? Okay, no, that leave it. So let us see, children. So first, it's very important to us to learn what actually wave is. What actually wave is. Children, to understand this, even if you want, you can do this. You can just take some water in a tub, in a bucket, in a glass also you can take. Okay, now fine. So after that, just try to touch that water with your finger. Then what happens, children? Yes, water will get disturbed, right? There some ripples are formed. So scientifically we can say ripples, or else we can simply say disturbance. But whatever the ripples which are formed there, do you think that they will stay there only, the point where you are disturbing? No, they will spread in all directions. Am I clear? Yes. So here water is a medium. Then we are touching, means what we are doing? We are creating a disturbance. So that disturbance can travel in all directions with equal speed. So this disturbance produced only, we can call it as a wave. So let me repeat once again. The disturbance created in the medium which can travel in all directions with equal speed is called, what actually, children, is called wave. Actually, regarding wave here, as I told you that wave, so disturbance, it is a disturbance. Where it is created, children? Disturbance, it must be in the medium only. Children, this medium might be, again I am telling you, it might be a solid, it might be a liquid, it might be a gas, it can be anything. So there must be some medium, children. But regarding the this what we can say disturbance, so we need to remember one important thing. So whenever wave is propagating, children, molecules or particles of the medium, they do not move. Very important. So particle of the medium, again I repeat once again. So whenever a wave is propagating, children, particles of the medium, they do not move. Rather, they can vibrate from their mean positions. Still, it's very important to be noted it is. So during the propagation of wave, is that clear, children? Mean position, this point has to be noted, has to be remembered. It's very important, very important. So whenever wave is propagating, particles of the medium, they do not move, rather they only can vibrate from their mean positions. Am I clear? So this is in a simple manner about a wave. It's a basic point regarding the wave, children. Okay, fine. Now according to our portion, according to our syllabus, we will see the types of waves, children. It's very important. Now we see the types of waves, children. But the thing is that based on what we are going to classify the waves, children. So here we are going to classify the waves into two groups based on whether they require material medium for this propagation or not. Am I clear? Fine, children. So here based on that, actually we have, children, we have electromagnetic waves. Simply I will write EM waves. Children, already we discussed this electromagnetic waves where in electromagnetic spectrum chapter 6, where there we discuss actually. Okay, na? So links will be given in description, just kindly go through it. Okay, fine. So electromagnetic waves, and another one is mechanical waves. Another one is mechanical waves. So children, so what are electromagnetic waves? What are mechanical waves? Children, here, what are mechanical waves? The waves which require a medium to propagate, means without medium they cannot travel. So medium is mandatory. Such a waves are called mechanical waves. Means here need medium, very important. Need medium. Again I am telling you, it might be a liquid, it might be a gas, it might be what we can say solid also. What it will be. So medium is needed actually. But whereas for this here, electromagnetic waves do not need medium. Do not need medium. Am I clear, children? So this is based on whether waves require a medium or not for this propagation. Am I clear? Fine. Now, so regarding mechanical waves, let us go a little bit depth, children, actually. Okay, fine. So here, mechanical wave. So whenever this mechanical wave is propagating, the best example, what we can say? Sound. What are the examples for mechanical wave, children? Yes, sound. Sound needs medium for their propagation. Okay, whereas radiations, okay, light can travel in the form of electromagnetic waves. Is it clear? Fine, children. Now, children, as I told you one important point, what is that? During the propagation of wave, particles of the medium, they do not move. Rather, they will vibrate from their mean positions. Okay, they don't move. They will be vibrating from their mean positions. So, based on that, how they will vibrate? Either they will vibrate parallel to the direction of propagation of wave or perpendicular to the direction of propagation of wave. So, based on that, again, these mechanical waves classified into two categories, children. It is the transverse waves. So, just it is based on what? How they are vibrating. Children, first suppose if the wave is propagating in the medium such a way that the particles of the medium, they are what we can say vibrating parallel to the direction of propagation of wave, parallel to the direction of propagation of wave. Such a wave is called longitudinal wave, which means what? So, during the propagation of longitudinal wave, particles of the medium vibrate parallel, very important. So, they will vibrate parallel to the direction of propagation of wave. Whereas transverse wave, children, so in these the particles of the medium vibrate perpendicular, very important. So, perpendicular to the direction of propagation of wave. So, in exam they may ask a question, what is a longitudinal wave? The wave in which the particles of the medium vibrate parallel to the direction of propagation of wave. Such a wave is called longitudinal wave. Then what about transverse wave? The wave in which the particles of the medium vibrate perpendicular to the direction of propagation of wave. Such a wave is called transverse wave. Children, during the propagation of longitudinal wave, children, so compressions, very important. Compressions, whereas rare factions are formed. Rare factions. Compressions means what, children? The region where there is a more molecular density. Whereas rarefaction means what? The regions where the molecular density is very less. Come to the transverse wave. During the propagation of transverse wave, children, so here what happens here? Crusts, troughs are formed. Crust, trough. What is the crust, children? It's a point of maximum displacement. Trough also point of maximum displacement, but this is upward direction, this is a downward direction. Okay, children. So, this is in a simple manner about this. And example for a longitudinal wave. So, children, it's very important. So, sound can propagate in air. Strictly I am talking about air, children. Strictly I am talking about air. So, sound waves in air can propagate in the form of longitudinal wave. Whereas under transverse waves, what comes children here? Light waves. So, light waves comes under actually transverse in nature. Don't get confused. Some children may get confused. Sir, here you said that light comes in electromagnetic waves. Again, you're talking about the transverse. I'm talking nature, by nature. Because when the light is traveling, it is consisting of electric and magnetic field. They will be oscillating perpendicular to the direction of propagation of wave. That is the reason why light is considered as to have a transverse in nature. And one more important point regarding longitudinal waves. Longitudinal waves can travel through solids, very important, solids, liquids, even through gases also. Very means longitudinal waves can propagate through all types of the medium. But transverse waves are not like that. They are very special, right? So, transverse waves can travel through air, yes, as light is passing, and on the surface of liquids. I can say on the surface of water. On the surface of water only. On the only surface of the liquid only, transverse waves can be produced. Okay, children. So, this is what actually, children, once again telling you. So, waves are classified into two groups based on whether they require medium or not. So, electromagnetic waves, they do not require medium, whereas mechanical waves require a medium. So, based on how particles will vibrate during the propagation of wave, based on that, again here we have two classifications here, longitudinal wave, transverse wave. What is the longitudinal wave, children, here? The wave, what we can say, the wave in which the particles of the medium vibrate parallel to the direction of propagation of wave is called longitudinal wave. And here in the longitudinal waves, compressions, rarefactions are formed. The best example, so sound in air can form in the form of longitudinal wave, And longitudinal waves can propagate through solids, liquids, gases. And come to the transverse wave, the wave in which the particles of the medium vibrate perpendicular to the direction of propagation of wave is called transverse wave. So in a transverse wave, children, crust and troughs are formed. The best example is the light comes in a transverse waves. Okay, so transverse waves can propagate through air, and they only can propagate on the surface of the liquids, but not through strictly solid. They are not. It's a very, very important. Is it clear? Just copy it and we will discuss. So when we learned that sound in air can travel in the form of longitudinal waves. So now we will see some terms related to the wave actually. Okay, just you copy it. Children, as we know that, so strictly we are talking about mechanical wave only, that's fine. So whenever a wave is propagating through the medium, we know that molecules, the particles of the medium vibrate from their mean positions, either parallel to the direction of propagation of wave or perpendicular to the direction of propagation of wave. Try to understand. Means, for example, here is its mean position. Either it may go right side or left side. Means till what maximum displacement it has. This only we can call it as a amplitude. Or else, if a wave is propagating like this, let us say, so this particle of the medium may go up or down. So this maximum displacement from its mean position is called amplitude. So here the first term which related to the wave is, what is the amplitude? Is very, 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 very important. So this I'll try to show with a diagram so that you will have better clarity. So let me show you with the clarity this one. So here is displacement distance graph, children. So let us say wave is going in this direction. So it's a mean position. So vertically till what maximum displacement is going, this only we can call it the amplitude, either vertical upward direction or downward direction. Is it clear, children? What is the amplitude? The maximum displacement of the particle from its mean position on either of side is called amplitude. Is it clear? Fine. Now the second one is time period. The second one is time period. Very, very important. Children, if you want to define a time period, you know. So again I'm telling you. So to define amplitude, just we have taken a displacement distance graph, but a time period, children, here we need to take a time here. So displacement versus time graph. Displacement versus time graph. Now, so this one. So here is a half wave, here is one more wave. To complete this wave, children, some time is taken, right? So let us say 0, this will be t. So time period. So children, what is the time period? The time taken to complete one wave is called time period. Is it clear? Fine. And the next term is, so frequency. Children, so like this, how many waves are formed? Number of waves are formed. But we have to calculate how many number of waves are formed per second. So the number of waves produced, produced per second is called frequency. So which means what here, children? Frequency is a number of waves produced per second is called frequency. Children, so frequency is a reciprocal of time period, because if more time is taken, then definitely less number of waves are formed. Okay na? So frequency is a reciprocal of time period. The SI unit of frequency is, children, hertz. So hertz is a SI unit of frequency. Is it clear? Fine. Actually, one more very, 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 very important. What is that? Wavelength. Children, wavelength. It is represented with a lambda. So to discuss about the wavelength, children, we need to take the displacement distance graph. So then this time period is going to be there here. Displacement distance graph. Children, again I'm telling you. For example, children, here, so to form a complete wave, okay na, the time taken we can call it the time period. In this given time period, don't you think that wave can travel some distance? How much distance it can travel? From here to here only, right? So this distance traveled by a wave in one time period, children, very, very important, very, very important. So here is called wavelength. Okay, fine. Now children, let us see wave velocity. So this is a point actually where many students will have confusion. So wave velocity. So it is the capital V or small v. Okay, capital V we can take. So what is the wave velocity, children? See, velocity is what actually, if it is going in a straight line path, distance, displacement both can be taken as same actually. So distance per second means distance traveled by the wave per second, children, try to understand. But whereas the wavelength is what? Distance traveled by the wave per one, what is the time period? Time period means complete, is a fixed value it is. For a given wave, lambda is fixed for a given wave. But where is the wave velocity? It depends on the medium. In a 1 second, it may travel more, it may travel less. Am I clear? Fine. So here, distance traveled by the wave, distance traveled by the wave in 1 second, children, in 1 second, try to just notice this difference, in 1 second is called wave velocity. And here we have an important relation between a wave velocity, frequency and a lambda. What is that here? Wave velocity is equal to frequency into lambda, So children, these are the important terms related to the wave. Just kindly note down. Children, so now we will discuss about the speed of longitudinal wave in air. So how to calculate the speed of the longitudinal wave? So children, so longitudinal wave in air is nothing but what actually? So sound only. So speed of the sound in air. So here speed of longitudinal wave, let us speed in air, children, strictly we are talking about the in air only. Children, here whenever longitudinal wave is propagating through air, there won't be any changes in a heat actually. So heat remains constant. So there is no exchange of heat actually. Okay, fine. So this can be given by V is equal to square root of gamma P by rho. Gamma P by rho. So what is the P here? Pressure. D is a density of air. Gamma is what, children? So gamma is a ratio between specific capacity at a constant pressure to the specific capacity at a constant volume. For air, its value is 1.4. Now children, on which factor does the speed of sound in air depends? Speed of sound in air depends, children. So let us try to list out the factors on which speed of sound depends. So first one, children, here it is temperature. Very important. So here speed of sound depends on temperature. How does it depend, children? For every 1 degree Celsius rise in temperature, the speed of sound is increased by 0.61 meter per second. So if you go on increasing the temperature by 1 degree Celsius, the speed of the sound is increased by 0.61 meter per second. Is it clear? Fine. Now second one. So it is the density. So children, speed of the sound is inversely proportional to the square root of density. As the density of the air is more, then obviously what will happen? The speed of the sound is decreased. Fine. Third factor is humidity. So children, speed of the sound is proportional to the humidity. Why? If humidity is increased, the density of the air decreases, due to which what will happen? Speed of the sound will become more. Okay, fine. Now next, the fourth one is direction of wind. So direction of wind, children. So here in the direction of wind, speed will be more. Opposite direction of wind, speed will be less. So these are the important factors on which speed of the sound depends. And here on which factor it does not depend, children. So this is also very important. It does not depend. So when I say first factor, you may get confused. What is that? Pressure. Because people will see the formula. They will say that, sir, in a formula pressure is there, but how can you say that it doesn't depend on the pressure? Children, if you go on increasing the pressure, what happens? Simultaneously, proportionally, density also increases. If you decrease the pressure, density decreases. If you increase the pressure, density increases. Which means what here? P by rho, this ratio is always remains constant. Hence, there is no impact of pressure on a speed of sound in air. Okay, fine. And the second one is what here? Second one is frequency. So frequency, and even you also can say that so wavelength. and even amplitude also, even amplitude. So these are the factors on which speed of the sound depends and speed of sound doesn't depend. Here you may get a one doubt, sir, actually you wrote about the speed of longitudinal wave, but why are you talking about the sound here? Children, so sound can travel in the form, in air, in the form of longitudinal wave. That is the reason why we have discussed here. So just copy it. First wave. So children, the best example, the waves produced in a stretched string, right? Stretched string are the best example for this. Am I clear? Fine. So how can we calculate here? That is V is equal to square root of T by M. So children, here what is a T, what is a M? So here the speed of transverse wave produced in a stretched string depends on mainly here two factors. One is T. Children, here T is not tension, sorry, T is not temperature, it's a tension only. Okay, okay, fine. So here T is a tension produced in the string, and M is what here? Linear mass density. Very, very important. Linear mass density. Linear mass density. Is it clear, children? Okay, fine. So just copy it. So here is a light waves and here is a sound waves, children. So the first point under light waves, children. So here light waves belongs to the electromagnetic waves. So these are electromagnetic waves. Whereas sound waves are mechanical waves. So which means what here? Second one. So light waves can travel through vacuum, children. Very, very, very important. Can travel through vacuum. But whereas sound waves do not. They do not travel through vacuum. Is it clear? Fine. And here the speed of light waves, children. Strictly I am talking in air. In air it is 3 into 10 power 8 meter per second. Am I clear? Fine. Whereas here the speed of sound strictly in air only, children, how much it is? Approximately 330 meter per second. So now fourth point, very, very important. So what is that actually? The wavelength range of the visible light, in the order of 10 power minus 6 meters. Whereas the wavelength of the sound, children, in the order of, I can say it's a 10 power minus 2 to 10 meters. Okay, fine. So here last point which to be remembered regarding light waves, that is the nature, children. So these light waves are transverse in nature. Whereas here sound waves are longitudinal in nature. So these are the important differences between light waves and sound waves. Just copy it, then we'll proceed. So now, children, we are going to discuss the very important topic in this unit, that is what actually an echo. So we discuss what is an echo and what are the conditions to hear the echo properly and its application. Children, before that, let us recall about reflection of light once again. Children, what happens when light strikes a surfaces, children? We know that it bounces back, and there even we learned about the laws of reflection also. So similarly, whenever sound strikes any surface, it might be a smooth or rough in nature, that sound gets reflected back. This is very, very important. So that is, we can call it as a reflection of sound actually. So same thing. So whatever the light, how it will obey the laws of reflection, similarly even sound also obeys the laws of reflection. So now let us see once again what happens when, in detail let us see, children. So when light strikes any obstacle, let us say any distant obstacle, what is going to happen? Let us see once again. For example, children, here let us say here is some obstacle, a distant obstacle, let us say that. So it is an obstacle. Let us take the distant obstacle. Distant. Say obstacle, it might be a wall, it might be a cliff, so it might be any tower, anything which will try to stop a sound, let us say that. Okay, fine. Now here is a person who is going to make a sound. So let us say here is a source. So the source of sound, such as that D is the distance between the obstacle and source of sound. Now the moment when person makes sound actually, children, he can hear, or another person, or he can hear two sounds actually. You may get surprised. Sir, he's the one only making a sound, so he should hear only one sound, right? No, children, he can hear two sounds. So one sound is the original sound, whatever he is producing. Am I clear? For example, if right now I am talking, means whatever I am talking, I am able to hear. So this original sound can be heard by this person. That is the one. But what is the next sound? That is a reflected sound. Let us see here. So when this person makes sound, children, so this sound will travel towards an obstacle. This we can call it as a incident sound. Incident sound. So when sound strikes any surfaces as like a light, it gets reflected back. It gets reflected back. This one we can call it as a reflected sound. This one we can call it as a reflected sound. Children, these reflected sound only we can call it as an echo. These reflected sound only we can call it as an echo. But children, can we call all reflected sounds echo, children? No, we cannot call. Children, let me tell you one important point. All echoes are reflected sounds only. But all reflected sounds, we cannot call it as an echo. Don't get confused. First of all, let us see once again. What is an echo? Children, yes, echo is nothing but the reflected sound only. So, the reflected sound heard from a distant obstacle after original sound has ceased. I mean what here? So, original sound completely should get vanished. After that, whatever the reflected sound which we are able to hear is called an echo. Is it clear, children? Okay, fine. Again, I repeat once again here. So, the reflected sound heard from a distant obstacle after original sound has ceased out. Means, whatever he is producing, that should be stopped completely. After that, whatever is reaching our ear, what that only we can call as an echo, which means what? There must be a clarity. Otherwise, what happens? You may get one doubt. Sir, what happens, sir? Yes, otherwise what happens? This original sound and reflected sound, both will reach our ear. We cannot hear the sound properly. There won't be any clarity. So, there will be a superimposition between what actually? Original sound and a reflected sound here. Okay, children? Fine. Now, how to calculate the, very important, how to calculate the distance between the, again very important, how to calculate the distance between the obstacle and the source of sound. Children, what is the speed formula? So we know that speed formula is equal to, we know that it is a distance by time. Distance by time. So what is this time? The time taken to hear the echo. Now children, speed is V. So now distance is d, time is t. Is it the formula? No, children, it is wrong. You may get a surprise again, sir. Why? How can you say it's wrong? The distance is d only, time is d. But here try to understand. In this time t, the sound is going forward distance d, again coming back, which means what? Forward d plus d is how much, children? 2d. So the distance traveled is 2d. Children, V is equal to d by t, that is general formula. V is equal to 2d by t, this is the formula for an echo. Very important. Okay, children, fine. Now, let us discuss the conditions to hear the echo in a proper manner. Okay, children. So, the first point, children. So, here, this original sound is going, striking the obstacle, again coming back. So here means there must be some time gap, definitely. So how much? What is the minimum time gap between original sound and the reflected sound, children? So that should be, children, I am talking about the minimum time. The minimum time is how much? The minimum time is 0.1 second. Here you may get one doubt, sir, why only 0.1 second? Because the reason is that a sensation of sound persists in our ear about 0.1 second. Means if less than this time actually, if any two sounds will reach our ear cannot differentiate which one is the original sound, which one is a reflected sound. So there must be a time gap of 0.1 second. Is it clear? Fine. Now the second point is that what should be the distance between an obstacle and a source of sound? Children, this distance is different in a different medium. First, let us see what is the minimum distance required in air so that we can hear the echo properly. So, I am talking in a air, children. So, as we all know that the speed of sound in a air is 330 meter per second. So, according to this only we are going to calculate. Children, we know that V is equal to 2D by T. From this, T is equal to, we can write we need to calculate the distance, right? So, here children, so from this D is equal to Vt by 2. Let us substitute 330 into 0.1 by 2. Children, if you can calculate, you will get it as a 16.5. So, approximately we can take as a 17 meters. Children, so very important. So, what is the minimum distance? What should be the minimum distance between an obstacle and a source of sound so that echo can be heard clearly? So, what is the distance, children? It should be 17 meters. Is it clear? Fine. Now, children, for suppose, okay, I am the person, I am standing in front of a wall at a 20 meters distance. I make a sound. Can I hear the echo? Children, think properly. Can I hear the echo? For suppose, if I make a sound like this, hello, like this, can I hear the echo? No, because whatever the sound which I am producing, it may not reach obstacle only. Of course, you are standing more than 17 meters, but still this virtual sound has to reach the obstacle, should get reflected, and that should be heard. So children, whatever the sound which we are producing, that should have enough intensity to get reflected back and should be heard clearly. Is it clear? Fine. Means what here? Sound should have enough intensity. Sound should have enough intensity. Sound should have enough intensity. And one more thing, children. For suppose, let us say A is the size of an obstacle and lambda is the wavelength of the sound. So here the size of an obstacle should be very much greater than that of the wavelength of the light. Sorry, not wavelength of the light, wavelength of the sound. Okay, children. So here these are the 4 conditions to be obeyed. Then only what happens? We can hear the echo properly. So children, these are the conditions to hear the echo proper way. So let us recall once again. So there must be a time gap between, minimum time gap can be more than this also, 0.1 seconds. And in air especially, children, in air especially, what should be the minimum distance? 17 meters. And here sound should have enough intensity so that it will, the reflected sound can get reflected in a proper way and can be heard. And the size of the reflector should be very much greater than that of the wavelength of the sound. And here when I say that the minimum distance in air is 16.5 meters, that is around 17 meters. And you may get one doubt, sir, what if it is in air or water? So even let me tell you here, if it is in a water, children, let us check what should be minimum distance required in a water. So for water also let us check, because this is very important for examination point of view also. So approximately in a water, the speed of the sound is 1450 meters. Children, it varies from, because what we can say, river water, sea water, the density matters there. So completely velocity also differ, but an average we are taking. Okay, fine. So T is equal to 0.1 second. Let us take this formula. D is equal to Vt by 2. Substitute here. It is 1450 into 0.1 by 2. So this is going to be a 145 by 2. So this is 72.5 meters. Look at here, children. So this is the minimum distance needed to hear the echo in air, whereas this is the minimum distance to hear the echo in water. So what I mean to say that here, in a different mediums, the D value will be different. What is the reason? Because we know that the speed of the sound is different in a different mediums. Okay, children. So this is about actually an echo and the conditions. Just to copy it, we will see the applications. So we see the applications. Okay, children, fine. So in the first point is that this echo method is used in radar. Children, what is a radar full form? It's examination point of view, it's very, very important. radio detection and ranging, and whereas second one we also use in sonar. Children, what is a full form of the sonar? This is sound navigation and ranging. So in sonar also we can use. Is it clear? Fine, children. And even children even see, try to understand. So in these two techniques we are going to use ultrasounds, very very important. So ultrasound. So why are we using ultrasound, children? We know that ultrasounds are the sounds with the frequency range 20,000 hertz, right? Yes, so that's the 20k hertz. Why are we using ultrasounds only? Why not others, children? The important point regarding the ultrasound is that here, first of all, these have high directionality, which means what? They can travel through the medium without getting deviated. That is the first point. And the second point, so as these sound waves have highest frequency, so they do not absorb the medium through which they are traveling, and they are confined to a narrow beam in an easy manner. So because of these three reasons we are using ultrasounds. I mean clear? That is the ultrasonics. Is it clear? Fine. So even children, if you can see bats, so here bats and even dolphins can produce ultrasounds. Try to understand. Even dolphins, they will produce ultrasounds to prey or to catch the prey. What way? For example, you think that I am a dolphin, so this 360 degrees I don't know where my prey is and I am just feeling hungry, so I produce these ultrasounds, and from whatever the direction, if I can get the echo in a less time, so I think that yes, so this side it is there, so I will go and attack. So that is what. So even how a bats can, so bats continuously they will producing the ultrasounds. You know that very well, bats they cannot see the things. Am I right? So they will produce the ultrasounds. So as they are going, these ultrasounds will go faster than those bats, and if any obstacle is there, gets reflected received by the bats, so that they can feel that yes, some obstacle is there, then definitely they will move from a side. Okay, now fine. And here next, the fourth one is that ultrasonography. So this is a it's a technique which is used in a medical field to see the whether internal organs are working properly or not. Okay, fine. And the fifth one is that echocardiography. So with which, so we can see the function. Of heart, whether is it working properly or not, are there any problem or not, are there any blocks or not. So all these things can be heard. Okay, now so children, in exam they don't ask you to explain how bats can see. In a simple manner they will ask you to write the applications of the what we can say echo. And mostly, and one more point here, they may ask you, why are we using ultrasonic waves only? Why are we using ultrasound only? Why not other? Because of three reasons. They have high directionality, they can be confined to a narrow beam, and they are not absorbed by the medium. So these are the what we can say applications of the echo. Okay, children, fine. So, and children, so what we can say, this session onwards, our team decided that, so at the end of every session we decided to give one homework question, so that you have some practice. Okay, children, so let me give you one homework question, children. So just try sincerely, it's very very important. So it is a homework, it is for you. Okay, today onwards, after every session, so you will get a one or two homework questions. Today I will give you only one simple question. So the thing is that, children, so here is an obstacle. Okay, na? The person is standing here at a distance of 50 meters. The speed of the sound is 330 meter per second. Then find the time in which you can hear the echo. Children, again I repeat your homework question. The person is standing 50 meters from an obstacle. Okay, he makes sound and the speed of the sound is 330 meter per second. Then what is the time in which the person can hear the echo? Okay, just you can try this numerical, and don't forget to comment your answer. Is it clear, children? Okay, so these are the topics of Unit A. So in the next class, we are going to cover the units of what you can say a topic which are there under the Unit B. Okay, children. Thank you so much. All the very best.